Good morning. My name is Gianluca Cusatis, and I will be chairing this opening plenary lecture of the Biot-Bazant conference. And it is my pleasure to introduce our opening plenary speaker, Professor Zdenek Bazant, who was born and educated in Prague, where he obtained his PhD in 1963. Professor Bazant joined the Northwestern in 1969, and he has been a Murphy Professor since 1990 and McCormick Institute Professor since 2002. Professor Bazant was inducted in several national academies, including National Academy of Science, National Academy of Engineering, the American Academy of Arts and Sciences, and the Royal Society of London, and many other national academies around the world. Is also the recipient of the Austrian Cross of Honor for Science and Arts. He has been given 70 honorary doctorates in many different universities around the world. He has been awarded many different medals from many different societies, including the SME medal, the SME Timoshenko, Nadai, and Warner medals, AC, von Karman, Freudenthal, Newark, Bio, Mindlin, and Kress medals. And as a matter of fact, he basically has been awarded all the medals that are available in our field, other than the medals that has his own name. Indeed, Professor Bazant, the AAC established a medal, Professor Bazant's medal for failure and damage prevention in 2015. Professor Bazant is one of the most cited authors in our field, and he is the author of more than 500 publications, peer-reviewed journal publications, and is the author of 7 books on topics spanning from concrete creep, fracture mechanics, quasi-ablative fracture mechanics, statistical fracture mechanics, and plasticity. And with this, I'll give the floor to Professor Bazant. Zdenek, please.
First of all, I wish to thank the organizers for affixing my name next to Biot's. What an honor to be named next to Biot's, the giant who founded poromechanics, and besides making major contributions to finite strain, to buckling of three-dimensional bodies, to geological strata folding, viscoelasticity, and so forth. So to my subject, I will discuss poromechanics, actually in unsaturated poromechanics, which has been a neglected subject. And it is of major importance for concrete, especially for long term. I distinguish collaborators, but I prefer to acknowledge them at the end. So what is the challenge? It's a grand challenge. It is century-plus prediction and extrapolation to that size, to the time. I wish to begin by showing a record of deflection histories of deflection versus time in logarithmic scales of 28 of 71 bridges which we deflected, collected at Northwestern about 12 years ago, and with the help, of course, of Rilem committee, which I formed at the time. The first bridge, KB Bridge in Palau, was an event which had a major impact. It deflected it was a world record span at the time of a pre-stressed box girder bridge, 240 meter span, and deflected by 1.61 meters in 18 years. had to be restressed, and during that it collapsed and killed more people. But you see a number of bridges which do the same thing, and I could show 3 plates like this from Europe, from Asia, from many places, and they have one thing in common. The deflections don't end with a finite value, which was assumed until not too long ago, but they continue in a logarithmic scale in time. Really straight, and we can be assumed they will continue much longer. These records do not exceed 30 years, but the extrapolation is actually straight line again. Now for the KB bridge, the first one, here is the deflection curve in linear scale, 1.61 meter. It was predicted by B3 model accurately. We developed at that time, but it was underpredicted by codes applicable at the time, JSC, ACI, CEB, grossly, about 30 or 20% of the actual value. The same is plotted here in the logarithmic scale. You see again the straight line extension at the end. It was analyzed in detail, and we also, of course, had to analyze pre-stress loss, which was very interesting since it was found that it was not like in design we assume about 20 to 25%, which is tolerable, but it exceeded 50%. These are measured pre-stress values when they bare the tendons and measured the retraction, and these values are far more than assumed in the codes. On the other, with B3 model recalibrated on that concrete, it was reasonably predicted. This is the same in logarithmic scale, and this has source, of course, in creep of concrete, but also, and that I will not be able to discuss, in relaxation of steel over decades, which surely happens because of viscoplasticity. It cannot be explained by creep of concrete only. So the main problem is that we need to extrapolate. The extrapolation is huge. In contrast to interpolation, where we have data covering the whole range, we cannot use empirical procedure. The time extrapolation is to more than 100 years, but not only time, we need to extrapolate in size, because we need to reach real sizes in structures which are far bigger than was in the lab. So, for example, in our database collected by mainly by Mia Hubler at Northwestern, or expanded by her, we have about 4,000 test curves from around the world. 95% of them go to 6 years duration, 99% to 12 years, and there is one data point for 18 years. As for size, 99% of data deal with specimens less than 16 centimeter thickness. But in design, we need to have meters thickness. Actually, the Polar Bridge was 14 meters deep beam, and slabs are often several meters thick. Now, this is very important because of drying. There's a diffusion problem, and I should point out that 1 millimeter slab of cement paste dries within about 8 hours to uniform humidity. 15 centimeter specimen takes about 20 years to dry. 40 centimeter specimen, about 150 years. And of course, when you go to 1 meter, it is millennia. So how to approach it? Extrapolation is difficult, but as with many problems, the asymptotes are simple. We often can determine short-time asymptote, but we can theoretically determine long-time asymptotes, and we can check it by other predictions, but not directly. So I will talk more about that. The key is to capture the hygrothermal behavior. Moisture has enormous effect on nanoporous materials such as concrete, hydrophilic. So first of all, we need a sorption isotherm for nano-macro-pore filling, which can be predicted theoretically based on statistics and thermodynamics on the molecular scale. There has been for a long time the BET, Brunauer-Emmet-Teller isotherm, which was also derived statistically by building up of layers of molecules on a solid surface of an adsorbent. And that was assuming just infinite wall and building up the layer on a surface such as cement paste. We know about 5 layers can be held on surface, not more. And each next layer is more weakly. Now there is a difference, however, which explains why BET isotherm works only for small humidities, but gross humidities predicts for high humidities, close to saturation. It has to do with the nature of filling of nanopores. So what matters for calculations of the adsorption is the surface exposed to vapor. The blank is vapor, and we show layers of 2 molecules thick, water molecule thick, which is about half a nanometer. And obviously, as the pore of a wedge type is getting filled, the area exposed to vapor is decreasing. Similarly, if you have cylindrical pores or in slits, a pore which is 3 millimeters, 3 molecules wide, allows some access of vapor and this contact. But if it's more than high humidity, it is filled, and suddenly it is not accessible to vapor. So that's a serious restriction which changes the statistics. So we proceed by generalizing the procedure used in deriving the classical BET isotherm. We consider adsorbent surface. Water molecules are being adsorbed or condensed from the vapor, and they also evaporate at the same time. Equilibrium occurs when the rate or expectation statistically of condensation is equal to the expectation of evaporation. We know these rates. They depend on hydration heats, the rates of adsorption, this is hydration heat of adsorption, gas constant, absolute temperature. This is hydration heat of liquefaction or condensation. And the properties are different in each layer, and what we do, we set up a system of recursive equations going all the way to infinity. They can be solved, and but we solve them under a restriction. The restriction is that the surface area in each next layer is decreasing. So you see, we imagine restraints here, given by some function beta as of the number of layers. Now, what function? It has to be power law. Why? Because the procedure is self-similar, because there is, after the first layer, there's no characteristic layer which will be standing out. And so it's a self-similar process which requires power law. So this leads to adsorption given by this theta, which is fraction of water content compared to saturation, which depends on humidity, also temperature, of course. And it is given by a ratio of 2 sums with a thermal coefficient, which is very important to change temperature, liquefaction heat here. And these sums, it so happens, can be explicitly obtained. They are well-known sums. They are called Jonquière function, which is readily available on Mathematica instantly, just like a sine function, and denoted as Li with the parameter. So that gives instantaneous evaluation of the isotherm and can be plotted and so forth. Now from this, we can get pore size distribution. That's actually the purpose. So first, let me show. It's a comparison of the mass content per unit volume of cement paste or concrete. In this case, it was cement paste. It is shown here for a very low water cement ratio, as about the limit in modern concretes. It is shown for the classical BET isotherm dashed, and this is our prediction, theoretical. And it is also shown for the empirical model GAB, which fits, predicts wrongly saturation, but fits also reasonably well. But if you change temperature, I will show later, it has major error. It cannot be used at all, actually. Now, from this, we can calculate the volume of content in the pores. And now what is convenient parameter is the volume fraction of surface of pores. Here, what is convenient is a pore width determined by humidity, pore humidity HF, at which the pore gets filled. And for knowing that, everything else follows. So that's beta F. So volume filled is expressed this way, and now we have here volume of the water per unit volume of concrete or cement paste, surface area of the adsorbed layers, also per unit volume of concrete. They are calculated from this parameter beta, derivative times already water filled layer, so forth, and finally the beta function. So this is all easily obtained and easily computed and can be constructed. So an interesting point is that we get somewhat different estimate of the internal surface area. The adsorption typically gives surface area of pores is about 500 meters square per centimeter cubic of the material. It actually implies that the average width of pores is about half a nanometer. Now, with this calculation, we get about 125 to 250, which implies average width of pores will be 1 nanometer, which is about 4 water molecule thickness. We show here some of results that we got, fitting the data of Bargel-Bouni from Paris on internal surface versus pore width. So this is the red data points, and classical data by Copeland from Portland Small Solution in Skokie next to us here, and this is the triangle points, and you see that predictions fit very well. Next, we need to address hydration, because that controls what happens over a long time, actually over a century, and that needs to be computed. There exists a well-known, highly regarded model of Garbozzi, which models hydration through a system of cement grains of some micrometer dimensions, thousands of them, as they hydrate. It's a very good program, but it takes a long time to calculate. It's a major calculation, and it cannot, for example, be used in fundamental programs in each integration point and each time of integration. We found at Northwestern a model which achieves nearly the same accuracy, modeling a continuum point under certain assumptions for what is in that continuum point happening in the microstructure. So what we have first day, we start with a cement grain, halide, C3S, water around. It starts rapidly hydrating, and within 4 hours there is a set. These layers contact each other, so this grows. And from 1 day on, we have the anhydrous grain, not yet reactive, is enveloped by a shell, so shell of CSH, calcium silicate hydrate. And that shell is slowly growing. So you see it here indicated by the particles, it densifies. And okay, so now The important point is as this grain grows, you greatly slow down the permeation of water molecules. Hydration can happen only if water molecule travels from water, this is water vapor. It must get through the shell to unhindered grain surface. There it reacts, and ions then must travel outside. There must be, of course, balance, so we need to water only by permeation of water. And this is highly impermeable, and the hydration, the time of diffusion grows with the square of the thickness. So if the thickness is few nanometers, it's practically immediate. If it grows to many micrometers, it takes a very long time because actually the permeability of CSH is surely much smaller than concrete as a whole, where preferably the diffusion goes through the largest pores. So here is the model, and here is the grain, shell, and permeation water molecules inside, balanced by ions going out. So obviously we need that's easily calculated. Mass conservation equation must be written, the gradient of the humidity or equivalent humidity throughout. Actually, pressures can be translated to humidity because it's uniquely related. Then boundary conditions, we have to calculate humidity in capillary pores, that's written here. Permeability is not constant, it decreases hydration because the structure is getting more compact with hydration degree. So its hydration degree is alpha, that's included here. It depends on humidity. I will mention later as humidity goes down from the vapor from 100% to 50%, it drops about 50 times. So that's why hydration is so terribly slow. And we need to calculate now the effective radius of the hydrated material, hydrated sphere. So these are spheres, z bar compared to the real radius of the sphere, because the spheres eventually contact and they cannot develop fully. So there must be a correction, which can be obtained asymptotically, matching between fully hydrated material, fully filled by hydration product, and this there is free. All right, and then I would like to show that it works. So hydration degree is shown here on the ordinate versus time. This is in linear scale, this is in logarithmic scale for various temperatures, for various types of cement, and for various water cement ratios. As the water cement ratios goes down, it goes much slower because humidity decreases more rapidly. And these data are followed well. I fitted as well as Garbozzi and Ben's model from National Bureau of Standards. All right, so pool humidity decreases by control by diffusions through CHH very shale. So this process is not determined, its rate is not determined by the chemical reaction actually, which is immediate, but it's totally controlled by diffusion through the very shells. Now the result is that water is withdrawn from pores, so there is self-desiccation. Even if the specimen is sealed, humidity is going down. Now, if you have lots of water in the pores, in old concrete, water cement ratio being 0.5, 0.6, self-desiccation used to be neglected because it was known long ago it goes to few percent down below saturation. But in modern concretes, where we use to achieve high strengths, we reach much less water. It is significant. A self-desiccation can go to 75%, can go now in some, we believe even out to 60% humidity in a sealed specimen. So we fit these data here for various water cement ratios, 0.5, 0.4, up to 0.2. So this will be the extreme, you cannot do less. This is actually the minimum required for hydration, 0.8 is the minimum. These are data for another set of humidities, water cement ratios, sorry. So that's one aspect, self-desiccation. So when the specimen is sealed, the vapor, the self-desiccation, decrease of humidity will occur below 1 saturation. This is the red. And this is humidity which is not yet affected by self-desiccation. So it is at the beginning small, and as it grows now, if the specimen is exposed like this on two surfaces from the side, this is the center line is on the left, this surface. There is a drying front propagating inward. This is error function, roughly parabola. So what happens that as you're drying from outside, hydration is slowed down, so solidification is smaller. Eventually, solidification will not even occur, like here. And the drying propagates in, and soon the solidification will stop, and everything is controlled by drying. So from here on, from this point on, solidification doesn't matter. Everything is drying. And it's different in thick specimen. I show here not a big difference, but it's actually huge. So this goes longer, the stage where you have no effect yet of solidification. Then drying starts here, then it penetrates as square root of time, roughly, and you have compared to here more solidification can happen in thick specimens than in thin ones. Much more can happen here. So this is much more sophisticated. And eventually, but this can take 20 years, this can take 100 years for specimens like 40 centimeters thick. Everything is controlled by drying, but not before that time. So this is a considerable complication. Size effect is major here, and you need to reconcile these two procedures to model it. Now it can be verified by plotting relative humidity versus time in a log scale. So what you have here is plots of relative humidity versus time for various fixed points in the specimen. So humidity gauge was placed at 12 centimeters deep below surface, 7 centimeters, 3 centimeters, something here. For one water cement ratio and as water cement ratio, there is a significant difference. And this is for different, this is everything for 60% humidity by different aggregate cement ratios. All this has to be included. Now, also what can be measured is the profile of humidity in the specimen. This is drying surface. Sorry, on the left, you have the center line. So you have distributions of humidity, and you immediately notice they don't look like in linear diffusion. It has a flat, and then it goes quickly down. That's a consequence of the nonlinearity of diffusivity, and from that, in 1972, already Nature reduced that northwestern humidity decreases almost more than 1 order of magnitude, actually, almost 2 orders of magnitude. These are data from 1960s from Skokie near us, hands-on, using Copeland gauge for a 6-inch specimen for various days. And these are data. This is the diffusion parameter, actually. That's how it's calculated, axisymmetric for various times. All right. So the next effect is that the self-desiccation causes shrinkage, and that's called autogenous shrinkage, happening by itself. Now, I will comment later, it is not caused directly by the chemical reaction, but as a consequence of the decrease of humidity. This was known for a long time. Troxel in 1950s and 60s measured that for concretes with relatively high water cement ratio, where the effect was not so pronounced, and later Brooks in Leeds measured up to 30 years. Now, what is interesting is that it's different what people thought until recently. It is generally believed that autogenous shrinkage strain stops in a few months. It was in the codes actually, but it actually goes for a century. You see here the picture in a log-log plot, and this is basically a straight line, which means the power law and exponent is about 0.2, not that small. If you take semi-log plot, it looks like this. It looks like acceleration in a semi-log. And you can discern the differences, different concretes at the end better. So this vehicle model has been modeled actually by Masulejad and Northwestern. And now I come to an inference from this. It took somehow some time to construct. It was generally believed that cement and concrete, due to always contract, that hydration is contractive. But that's true only on the nanoscale. The conclusion is that hydration actually on the scale of many micrometers or many nanometers from 1 millimeter is expansive, always expansive, and all the shrinkage that we see is due to self-desiccation or drying. Both decrease humidity, and that's one phenomenon, drying. All right, so I could say that's a new paradigm for hydration shrinkage. Hydration is expansive, and as far as we can see, it is the only way we can capture with one and the same model all these phenomena, especially drying shrinkage, autogenous shrinkage, with the same parameters. Long-term swelling of thin specimen underwater, which can imbibe water. I didn't put long-term swelling or short-term swelling of thick specimens, which are affected only at the beginning. Short-term negative autogenous shrinkage in sealed specimens, which is seen. Size effect on drying times, which is enormous. In my opinion, it is impossible to fit it under the assumption that hydration itself shrinks regardless of humidity. It must be effect of the change of humidity. So that's I proposed 5 years ago. There is lots of resistance to it. It's not completely not accepted generally yet, but I believe this is the phenomenon. If you didn't have these data, then theoretically you could go either way. It could be extraction, contraction by some general available models. Once you put numbers and measurements, that's the only way. All right. So now, what does it mean? How this expansion happens and why? So you have particles forming, and we start with a here's grain, which eventually grows. The CSH grows to two spheres in contact, and when they want to try more, they cannot because they overlap. You see overlap of these two circles. So what happens? But there is a structure. These particles are not free to move. They are part of a skeleton already. There are other particles. So it is resisted. What develops here is something like crystal growth pressure. It's actually exactly analogous. That pushes the particles attached apart, but resisted by the skeleton elastically or viscoelastically. And that's actually the expansion, because these shells cannot be accommodated freely, and the expansion, the growth causes expansion, and obviously it goes, as long as the diffusion goes, it goes for a century and more. So conclusion is all the shrinkage elastic, actually viscoelastic, because possibly because the viscoelastic even at this nanoscale there is somewhat debatable, because these are actually crystals. And It is due to decrease of pore humidity. More generally, if we vary temperature, we must speak of chemical potential, which is directly related. And that's, of course, offsets the hydration effect. All right. So now we must calculate diffusion. We must calculate diffusion in the cement shells, but mainly for fitting data, we must calculate diffusion for the whole specimen. I will not spend much time on this, although it is a big subject, but it's a highly nonlinear phenomenon that was found at Northwestern 1972. Nature at that time got the data from PCA on humidity distributions and evolutions by newly developed humidity gauge of Monfort and Copeland. We came up with this formula, which is plotted here. Diffusivity or permeability both decrease from 100% here down at a 50% humidity. At that time, we believe it's about 20 times smaller than the formula gives exactly that. And this is a guess down. Now, for modern concretes, we have many more data now with better humidity gauges, piezoelectric gauges. We conclude by the same reasoning that this formula does not need to change the form, but needs to change the parameters somewhat. Beta and R have to change. It gives a curve like shown the red one, which decreases more steeply. It goes about 50 times down here and surely goes to zero, because when concrete is fully dried, it has no water in it, there is no permeability either, but it also does not creep. Unfortunately, we cannot dry concrete without cracking it. All right, so from this we can formulate the diffusion equation, flux, gradient of humidity, conservation equation for balance of moisture, and then we calculate humidity drop. Now, humidity, turns out, is a much more convenient parameter for diffusion than water content, which was used before Nature's work with near Northwestern. Why? Because hydration changes humidity, especially in the original concretes with high humidity, very little. On the other hand, it consumes lots of water and changes water content enormously. So you have more complicated equation in terms of water content, than bigger errors than in terms of humidity. This is some unusual, because in all the other applications there is concentration of the mass diffusing. All right, or pressure as such, but this is relative pressure for humidity. Now, the free energy-based unsaturated poromechanics can be formulated. Here we are extending seminal work of Olivier Coucy, who died unfortunately at a relatively young age, in his 50s, about 12 years ago. He made major contributions to poromechanics, including unsaturated, in which didn't get the final model, but he works with Gibbs Helmholtz energy essentially. And but anyway, this was provided inspiration to us, these two papers. So we recognize the fact that Gibbs free energy of water in a unit volume of concrete is a sum of Gibbs free energies, all the phases. In atmospheric equilibrium, Gibbs free energy, or called chemical potential per unit mass, must be equal in all the phases. So you sum the masses times increments of chemical potential to get the total increment of chemical potential, which is the free energy psi of water concrete. Now, there are different phases. So first of all, we have porosity, which you must know. And then, by definition, what multiplies it is equivalent pore pressure, equivalent thermodynamically, although partial pressures are, of course, very different. Now, then we have a term for vapor, where this is multiplied but concentration of vapor within the pores relative to pores. So when this is 1, it means pores are fully filled. Then of liquid water, capillary water, that's the next term. Mass comes here because it's per unit volume is 1 over density of volume or liquid. Then surface area of the adsorbed layers. So here we must deal with the thickness adsorbed layers, number of molecular layers, 1 to 5 basically. We have pressure, which is the spreading pressure in adsorbed layers, which offsets the surface tension of the solid. It goes the opposite way. And 2/3 is because this is a biaxial stress. Third this direction, there is no stress. Similarly for the filling of the pore, but when you get to pore pressure in pores which are fully filled, this is called this is called hindered adsorption. And the pressure is called disjoining pressure. It is known it exceeds over 100 megapascal typically. And then we have triaxial stress. So instead of 2/3, we have 1/3. So this is accounted for. If temperature is varied, this term is essential, of course, change of temperature. So this can be all calculated. Actually, it's not terribly difficult. We have a program for this. And for free adsorptions, and we have the spreading pressure, which is expressed here for hindered adsorption. That sort of repeats in more detail what I just said. And for capillary water, where meniscus radius is essential, that's here. All right, so to get the equivalent pore pressure, we have terms which are shown here, which gives associated with autogenous shrinkage and drying shrinkage. So liquid water here, so this is the capillary part. Liquid water again here, this is adsorption, thickness of adsorption layer. And this is for the fully filled pore where you have disjoining pressures. So pressures can be calculated, and they are here. They can be calculated if you know the ratio of transverse and longitudinal pressure. That has to be estimated. So this we get finally to poromechanics, and the difference that this is an unsaturated poromechanics, which has not been really formulated before. Now, obviously, the poromechanical equations must have the same form as the Biot classical equations. So these are Biot's equations classically, and in his formulations, it was actually the pressure of liquid water in the pores like of sand, fully filled. Now it's a combination effective of pressure of vapor and adsorbed water and hindered adsorbed water, all these phases. This is only volumetric part, so this is stress in the solid, volumetric stress in the solid phase. This is in the liquid phase, equivalent pressure. Now, sorry, this is volume expansion of the porous material, epsilon, thermotherm, and zeta is effective expansion of the fluid phase. So what it means, that's a divergence of the increase of volume if the specimen is drained. So water can go freely out. So these are the parameters which are similarly conjugate. And of course, this equation, because all must fit the Gibbs free energy, must give symmetric equation systems. So B over K C over R must be equal as expressed here. And that and here B is the famous Biot coefficient, which gives us the change of volumetric stress in the solid due to unit change of equivalent pore pressure and no change of strain. So that's one parameter, and as a Skempton parameter here, but this is the most important one. It occurs in all kinds of calculations. Now, I must also say, because in bulk, sure, cement creeps, gives volumetrically too, because it's porous. So this solid phase compliance, 1 over K here, must be replaced by creep operator, and actually this R also. And that's well known how to do that. We use the same creep operator as obtained from all kinds of other calculations. And all these parameters depend on the degree of hydration, so they change with time. So it's another point which, if we degree of hydration, we can express it. Then one point I would like to emphasize, which is typically overlooked, and there are no test data unfortunately for it, is that when we come to saturation and increase the pressure of the isotherm is not flat. It would be essentially flat if concrete were filled by liquid. Then you could use the equation of state for water from STM tables, and you would predict a negligible slope because water is quite stiff by comparison. What is in reality, it goes up very steeply, probably as steeply as it does here. Of course, it's all irreversible, mainly with geometrical effects. And how can we explain? My point is that water is never fully saturated. I think it is impossible to saturate concrete fully. Why? Right from the beginning, of course, at the moment of set, it's saturated, but then solidification begins. So there are air pockets, and water can never be put back fully. The explanation of this isotherm is here. For example, if you have a pore which contains vapor and humidity is less than 1, you have equilibrium with positive meniscus here. This is liquid as pore, but you can have also equilibrium at big pressure here of water or steam. And then you have a negative Gaussian curvature is also equilibrium. And to fill this takes a long time, diffusion, and eventually to smaller and smaller pores, and probably it never happens in practice. Another example, there are many examples. 2 spheres at low humidity, there is a hyperbolic surface with positive negative curvature. At 1, they are equal, Gaussian curvature is 0, and at positive curvature it is negative, but still you have vapor around it. And there are many other situations like that. So concrete can never be fully saturated, and this was omitted in calculations first. So inside concrete dams, pore pressure has never been measured. Frustrated by this fact, in Berkeley, when I came there in 1969, I had a pipe, steel pipe, filled with water stretching over several floors. At the bottom, they put a plug of concrete, installed a gauge, and in 30 years, under this, they could never measure any pressure. It is known that if you heat concrete blocks to 30 degrees C, there was nuclear reactor research. They measured negligible pressure. They measured some pressures, but negligible. The same thing in a lab, we measured in a rigid steel container and so forth. All right, so next one needs to predict deformations. That includes shrinkage too. It has to do it from the hydration model and from the sorption isotherm and our NRV isotherm. So results are shown here for different water cement ratios, plotting water content percentage of the concrete volume or cement paste volume, depending on which data. So this is one water cement ratio, much higher water cement ratio. Recent data, not too old, I mean, from Paris, Borger-Booney data from Ilston in London. All these are fitted and predicted with parameters which fit all the data on that model. Next come autogenous shrinkage. Already said that it is goes probably forever in the logarithmic scale. So this is actually this is a semi-log plot published by Persson from Gothenburg. He measured for about 10 years, and it does not end as in a few months as assumed from linear scale plots, but actually goes and goes on and on. No plateau. They eventually has to be plateau because they find an amount of reactants, but they can be centuries away. So as far as we know, there is no plateau. Now this gets complicated when you put specimen in water. So that if there is water, shrinkage is prevented and swelling prevails. And that's actually where you need the assumption that concrete hydration is always expansive. Otherwise, you could not model swelling. So in thin specimen, water penetrates quickly in. There is no core left, so there is small expansion, can be big. Swelling here is big. This is swelling. This is shrinkage. Opposite signs. Okay, so there's a big expansion, and eventually, when time progresses, because there is moisture present, there is solidification. Creates vapor, and the solidification prevails even in specimens which are in water. So that's shown here why these curves are fitted. So please note, in a thin specimen, we have water outside, immersed specimen. There is drying progressing, but this is not affected and it's shrinking. Sorry, in a big specimen, not as I said thin, so slip of mind. So solidification will prevail and diffusion of water into the specimen will matter little. In a small specimen, in a wafer, it's obvious there is no longer unaffected shrinkage part with solidification. Water penetrates in, there will be no solidification, and then you get the swelling. So without this expansive assumption of expansion, you cannot model these data at the same concrete. Now then, of course, we must model creep. So that has been studied for 50 years. Now there are two basic models. One is solidification. Now the essence of solidification theory is that thermodynamically it's impossible to model it as a time-dependent material. There is no thermodynamics. One must assume thermodynamics can be modeled of material of constant properties, which means there are constituents which are non-aging. For example, CSH as such on a nanoscale is non-aging, and their volume is growing, or they are getting interlinked by polymerization, and that's works thermodynamically properly. There were, in computational mechanics, several models published in the term of nuclear reactor research, which did not take into account this thermodynamic restriction which comes out, and they actually violated second law. So that's restricts the form of positive law. Then to model over long scale, you need is a broad spectrum of relaxation times ranging from microseconds to years to decades. So we need a Kelvin chain to describe it, much more effective than integrals. And eventually there's one specimen which has a very small elastic resistance, basically flow. Now, and all this is controlled now by micro-prestress, how quickly it goes. Micro-prestress expresses another fact. It was mainly evident from so-called Pickett effect, discovered in Wisconsin in 1943, that if concrete humidity is decreased and is constant, specimen creep much less, actually by orders of magnitude. On the other hand, during drying, specimens creep 2, 3, 4 times more than at constant moisture content. So there is some transient effect. That can be modeled by recognizing that structure is upset or by internal stresses. These can obviously are enormous in disjoining pressure, disjoining pressures in hindered adsorbed layers. And this S is called micro-prestress, or if you prefer, you can call eigenstress, same thing. There is basically a relaxation equation, so we speak of relaxation micro-prestress. And the interesting point is, okay, microstress is built up at the beginning, then relaxes, but when there is change of moisture content, it increases micro-prestress. And what is also essential point that micro-prestress is a local stress, self-equilibrated in small volumes. It's independent of external load. External load does not affect it, also cannot affect it. It's driven by driving term, by changes of humidity and temperature. And now here I want to mention the point. At first, in the original micro-prestress theory, assumed it's given only by only the values of micro-prestress are affected, affect the viscosity. This is viscosity of flow and viscosity of the creep. Now, it was found by Jirasek and Havlasek that predictions in some cases were not good. And in fact, it gave for drying creep of very different specimen sizes reverse side effect. So side effect is always indicative, important to watch. And we found a way that to fit it was to add a term of which was shown here. Now it is shown in the next slide. That there is a dependence of S dot. Now, how to explain it? So one phenomenon like this is the Pickett effect that I mentioned. So this effect was explained, but only partly by microcracking and insufficiently. It was clarified finally by MD simulations done by Cinco and Ketten at Northwestern with me a few years ago. You have two solid walls modeled by molecularly. Then you fill the gap by water molecules shown here, and if water molecules are present because it's hydrophilic, creep is in a microscopic scale. We believe it's always shear creep. Creep is always sliding of these sheets, not widening or something. Okay, it creeps more, but what is important to recognize that if we make it move, which would happen due to drying or wetting, doesn't matter the direction of movement, you get much smaller viscosity resistance to this force. Intuitively, I imagine there is a energy surface which is wavy up and down, and when the energy surface of one face slices against another, it rides on the tops of the so there is much less resistance. It actually comes out from the simulations necessarily, MD simulations. So what it means that solidification, micro-solidification theory has to be corrected by eddy term in the circle S dot. And then we can calibrate for size effect on drying creep. And micro-prestress solution then is a similar same equation. It translates to thermal effects. That was actually modeled by Kusatis also. Now I show where we could not fit well before getting reverse side effect, at least for part of the time. Extended experiments of Bryant, which show for different thicknesses, for different concretes. You see this is 200, 240. And you will see we fit the side effect very well. For slabs, we do it for prisms, and for various environmental humidities, 60%, 80%, all by the same parameters. Always important to model everything by same parameters. Okay. We can also fit the data for different ages of loading. Concrete, so this is hydration effect together with micro-prestress. It actually, if you take only hydration volume, which was thought before, hydration goes on, but volume does not increase much after the first year. And to explain why there is an age effect after that, you need the relaxation of micro-prestress. As it relaxes, structure becomes more compact, less disturbed, it creeps less. And that goes for decades, for years. Now, another important phenomenon which is typically neglected in practice, thermal expansion for expansion. People still assume in general programs that expansion coefficient is constant, 0.12. Now we show the relative values here, and at various pore humidities going from 0 to 1. These are the data. Is a change more like 2 to 1. It's a big change, and we can fit it using our sorption isotherm. This gap isotherm cannot do that, GAB, empirical one, because it does not have correct thermal, it's not thermodynamic. And hygrothermic coefficient can be also modeled. Hygrothermic coefficient means change of humidity due to change of temperature in a sealed specimen. So again, you see that this model reasonably well. Gap theory cannot model this. Gap stands for Guggenheim, Anderson, and Bohr, de Boer. Now, another thing to check, we know that external load cannot cause escape of water from concrete or cement paste. It was shown already by Hansen in Stockholm in 1958 that you have two specimens, one loaded, one not loaded, and both are drying. You cannot tell the difference. There is a negligible differential calculation, but cannot really be detected easily by measurements. That's calculated. So model predicts no effect. Same thing for sorption. Isotherm, we know it's independent of whether there's compression or not. That's satisfied. You see negligible difference. Of course, if you expand it, we see some difference in calculations, but that's totally negligible. So that's an important check on all the models of moisture. By the way, this defeated the consolidation theory of concrete creep in 1958. It took time to sink in, but that was the end. At temperature changes, it's also modeled. Next, we deal with data. Data, unfortunately, are collected for different concretes. We can never get enough data in one lab, so we take data from the whole world, from many labs, measured on different concretes, of behaving qualitatively similarly, but quantitatively different. And people in different labs measure differently, and that needs to be corrected. They introduce errors, and needs to be sorted out. Now, it has to be corrected based on what we theoretically know. So theoretically, we know well the asymptotes, short time as well as long time. So you take short time, there is no characteristic time, and no characteristic time, which means that no, in a response function, any response function, if we take one or another characteristic time, we must get similar behavior, which leads to this functional equation. That's a functional equation happens to be easily solved. There is only one solution, and that's a power function with some exponent n. Please note, a limit of power function is logarithmic function, which is a power function of rate, so that's also okay. That's also admitted. So how can we measure it? Important is the initial behavior. So you have a creep curve which starts with a vertical tangent. It is difficult to say where the creep begins, what is elastic. Consider this pink strip. So it's about 1 or 2 days. So if we have other phenomena going on, inevitably autogenous shrinkage always goes simultaneously. We have two phenomena going here, creep and autogenous, they interact. We cannot say anything simple. But here in this range, autogenous shrinkage changes little. If you say this is drying we started before also will change little. So only one phenomenon, which is hydration driving cell desiccation. So there must be self-similarity. This must follow a power law. So we can fit a power law to the data, which is shown here. We conclude about 0.1. These are typical data. Please note here one aspect. What is creep? If you use a hydraulic setup, open a valve suddenly, then you get the specimen is loaded within 1/10 of a second or less. If you do it manually, which is widely used by spring type apparatus that may take 2 hours, even more to set up. So that gives huge difference in the initial deformation, initial creep, initial deformation. And if people report creep rather than total compliance, then it leads to great, which they often do. They only many people report only this creep, not the rest. That error is carried out all the way to infinity. It's a shift of the response curve. If you take it in a log scale, so this is typical creep curve in a log scale, semi-log scale, exponent. No, wait a minute. This is a log scale, 0.1 because it's straight line. So here is 1/10 of a second. This is the range of damping in vibrations, complex modulus, viscoelastic. So it's actually also known. It's and continues a straight line, and here up to what is in the practical testing. So first we try to fit in. That was done by Rasunejad. The power law to the initial data for 1 or 2 days, and it's a nonlinear problem. We use nonlinear optimization. It was running forever, very expensive computations, and did not always properly converge. Then we decided a different approach, realized that if the shift in strain is fixed, delta, and the corresponding shift in time is also fixed, so both are fixed, the rest of fitting is a linear regression. A linear regression runs immediately. That's very, very, very fast. So what we did, we do sampling and search. We assume all these combinations shown here. There's actually 60 combinations. Run linear regressions for all of them. Then calculate the coefficient variation square for each linear regression, and try and see which point minimizes. This red point here, minimize that and gives the values. And this is very fast. Even with these linear regressions, it's fraction of a second to get the whole fit, correcting the data. So I show one of many data which we corrected, and that will be published on the website of this Northwest University database. These are classical data of Wittmann, who measured on cement paste. That was considered very good because these curves fit a very nicely smooth line. But it does not fit power law, so there must have been error in the initial setup. And when we correct this law, we get perfect straight line, perfect law. So I think that's one of many validations which we have by minimizing this error of the regressions. One can check also how it works by comparing calculated versus measured values. If you don't make correction, you get measured values for initial data does not work well, as you see here in these plots. But after optimization, measured versus calculated goes as slope 1 and 1 here, where it must be if the fit is good. And this is for famous data from Berkeley, which are probably most accurate of all by Commandant and Polivka, my fellow countryman. Finally, we need to deliver something for practice. In practice, engineers have to design things quickly, and they need a code which gives them a total creep curve. So all the codes specify creep curves excuse me, creep curves in time, epsilon versus time. It's actually a very difficult proposition. It's much easier to know just incremental law and integrate by computer, but it does not give you enough insight for designers to see what's happening. And now you have all these phenomena intervening. You get all kinds of curves. So you must devise a formula which is explicit and easily calculated. And we are getting it for next model with B5. B4 is now a code, actually real recommendation, and ACR recommendation 2 for drying autogenous shrinkage. So the approach we are taking, that's done by Dunmes. We use partition of unity approach, combining two trends: autogenous shrinkage for a simple formula, and drying shrinkage simple formula, and they need to be somehow combined. So partition of unity gives a parameter here, but that parameter depends on time. This is shrinkage shape function, but that function depends on size enormously, drying half time, and that must be included. And if that's, and also depends on humidity, so that comes also here, this parameter. So there's 3 parameters coming into partition of unity. If you all 3, you get reasonably good shapes. Actually, it's surprising that it matches the data reasonably well, and we still have to do it for drying creep. That's a further challenge, but I'm confident we will have it soon. So that's the work of Dunmes. This is if you do autogenous shrinkage only, the B5 model looks like this. So with this, I'm coming to the end, but I would want to mention a broad impact. We all discuss CO2 emissions, major problem. Now it is well known, but not stated in public discussion, it's almost never mentioned, that production of cement releases now almost as much carbon dioxide as all the cars and trucks in the world. About 8% of the total emissions occurring today. And since the use of concrete is expanding in Asia, in Africa now too, this will surely grow a lot. So it has to be addressed in many ways. But one thing that would surely help if we can extend inadequate, woefully inadequate lifetimes of concrete structures. I showed it at the beginning. If you are doubled, then in the long run, we will greatly reduce the demand of cement. And that should be one objective. Unfortunately, engineers are often not concerned what happens in 40 years because nobody will get liable, but we should have this higher goal in mind. So misprediction of concrete creep is a problem here. Why creep? Okay, creep is never uniform. There's always a mismatch. Differential creep, differential drying, differential shrinkage, and that causes fracturing, distributed fracturing at first, eventually fractures. That leads to increase of corrosive agents and degradation of the material, and that's why the lifetime is ended in 20, 30 years instead of 150 years, as many departments of transportation typically require. And I want to mention also an afterthought. 132 years after Le Chatelier, 114 after Hatt had to discover at Purdue University the creep of concrete. The creep hydrothermal effects are now seen to be a much bigger challenge than anybody originally thought. I have actually been working on concrete intermittently, occasionally perhaps, but for 61 years. Now, what I see as a problem that should not be seen as a problem of mechanics only. It's a problem of material science, and so we in civil engineering have to do material science. But why this formula problem is not done in material science department, which have all the students educated properly in this kind of problem? There is almost no work on concrete in all the material science departments in the country. I think it's a problem. We should discuss it. And Europe is not too different. Much of this research is on civil engineering departments. So with this, I would like to acknowledge outstanding collaborators which helped me in this work. Juan Nguyen, a doctoral student near his graduation, who did much of the calculations, mathematically contributed or experimentally. Abdullah Dönmez, first as a student at Northwestern, then a postdoc, and now in Turkey, assistant professor in Istanbul, who did this data analysis and also the moisture studies. Then a major contribution from Saeed Rahimi Agdam, who graduated with a PhD and is now in Austin, making great salary with oil consulting firm, consulting mainly for fracking. Then Mohammad Rasulejad, who also got his PhD, and he was extremely good in big data analysis, aside from mechanics, and went as postdoc to do more machine learning such things. And last but not least, my outstanding and most respected colleague, Gianluca Cusatis. So with this, thanks for listening.
Thank you, Professor Bazant. So I encourage everybody to unmute so that we can clap, please. There we go. Let's make some noise. Excellent. Thank you, Professor Bazant. This was a great lecture. We do have time for questions. So if you have a question, put your name in the chat, and I will call you to unmute and give the question live. I know Professor Ulm has a question ready to go, so I'll let him go. Professor Bazant, if you can unshare, because Professor Ulm has to share.
Yeah, where is the share actually? Wait a minute.
It's on the bottom, the green.
Yeah, I don't see the green. Wait a minute, I have to escape, yeah, escape, right. And where is the share?
You want to share what?
No, unshare.
Oh, unshare. Stop share.
Oh, here, the red. Okay, I was looking for the green. Okay.
There we go.
All right.
So, Franz.
First of all, thank you very much for this.
I don't hear you.
You're muted. You're muted.
I don't hear you.
Yeah. Okay. Thank you very much for this tour de force of how many years of research? 50 with data which now almost spans a century. I want to, while I agree with many things what you have said, I want to challenge the notion which you said that hydration can only be expansive, meaning that the volume increases. And there's a whole school actually out there who is working on this here, and which I just want everybody to be aware of it and get your feeling about this. So if we think about hydration, we basically hydrate some material properties, some hydration products inside the system. They have a certain distance R. The energy in between them is defined by an energy U. Here's the distance. There's some equilibrium distance R0. At short distance, it's repulsive. So it has this shoulder here. And then maybe it has an expansive shoulder and here. And here. So yes. So for everybody, just to be aware that we're on the same page, the slope of this curve is basically the force. So this side here, here, this is an attractive. So it attracts basically.
These are grains,
right? The
or
material
atoms or molecules?
Grains, CSH grains. I'm talking about scales of 5 nanometers with high surface factors, whereas on the other side here, you have here some repulsion. Now, why is that important? Because when I think about the hydration, you start out, of course, hydrating into an empty space. So at some stage, I start out from here. This is my distance R. I hydrate here with a distance which is relatively large. So here, there's clearly a repulsion taking place. And I think that is correct. But at some stage here, our material will gel actually, and it will reach bypass a percolation threshold, beyond which the distance between particles is such that they are attracted. And ultimately, they want to come here to this equilibrium stage. So this is the way how we, people have started looking at this problem from a complete other perspective, actually from particle mechanics, backed up by results from Nonat, who has made measurements from by AFM with a functionalized tip, where he measured actually depending on the the concentration of portlandite in the solution, attraction or repulsion. So I wanted to challenge the notion that hydration can only be attractive, and thus also the very origin of the autogenous shrinkage. And I know this is very a controversy, but since we're here to discuss what we don't know or where we are sure about it, I want to ask you this question. Do you think, let's say, that we are missing something in our picture?
Professor Bazant?
Yes, I agree that theoretically you can have either expansion or attraction.
We
It
cannot,
depends which one prevails. But it is because of experimental evidence that you cannot fit all these phenomena with assuming that it's ever contracting. Now let me, I can couple my, wait a minute, my advanced. Okay, I prefer to work with pen. All right, so you have grains and they are growing, and eventually they grow like this, and they want to overlap, they can't. And that overlap starts happening at one day. And so it is easily understandable as another explanation that what prevails is behind this point that you showed on your diagram of the, you showed this diagram, behind this point where you are, so it causes that they go apart, they move apart, and then you have a skeleton. You can imagine like bars, and something like that, and each bar is getting thinner and getting longer, expanding. So the whole thing expands. That's how I view it. Now, Franz, both are possible, but you have to look at the evidence, because I show all these 5 phenomena that needs to be satisfied, and opponents of this question would have to show that this can fit those data. I don't believe that.
No, I
explanations
agree.
are possible.
So from a pragmatic point of view, if I take your point that you have all these different data, you are looking for a unified theory to bring all these things together.
That's the point.
I just want to lay out that there is another school of thoughts out there, which even though it is just more physics driven and is rejected by sort of the classical cement and concrete research community, is there and has a strong evidence experimentally, both experimentally as well as from simulations, advanced simulations for this hypothesis. But I agree with you. We cannot explain yet all the phenomena which you brought forward.
You cannot, but we can explain them. That's the point. I mean, I challenge the physics community to fit these data. They don't. It's theoretically possible. What you say is actually plausible, and I'm aware of it. But we have to abandon the possible. We have to accept the expansiveness, because that's the only way to fit the data. It's a possible explanation, one of possible theoretically.
Okay.
But
I take
fit
it.
of data shows this is the only one. That's my point.
Thank you. This was a very good start of how we want this conference to go, with different ideas and different discussion. So any other question for Professor Bazant? We do have a couple more minutes, then we have to move to the parallel sessions. Anybody? If that is not the case, Professor Bazant, thank you very much again for the presentation. And again, let's clap again. So unmute. Some noise. Excellent. Thank you, Professor Bazant.